Hello everyone. In this tutorial, we will be learning on internal working of HashMap. If you are not familiar with basic features of HashMap, please refer to the tutorial mentioned in the comment section below. Here we can discuss on the concepts used in HashMap like load factor, initial capacity, mode count, tree-fi, untree-fi, etc. What is rehashing and in which scenarios it happens? What are performance overhead and how it can be optimized in Java 8. HashMap implementation with linked list and red-black tree with detailed example. What is hash collision and how it can be resolved in Java 8. Different use cases on split shrinkage of bins in HashMaps along with frequently asked questions. HashMap is hash table based implementation of map interface. The difference between HashMap and hashtable is that it is not synchronized and it permits one null key with multiple null values. It does not allow any ordering, it is fail fast, and it works on the principle of hashing. It means it will do some logic to calculate hashing and reuse the same hashing for different operations, for example, for storing and retrieving. We can discuss in more detail later. An instance of HashMap can be initialized in four ways as shown here, using the default constructor, second with the map object, third with the initial capacity, and fourth with the combination of initial capacity and load factor. It can be stored in the form of array of buckets. We will call this as bins. Capacity is the number of buckets in the hash table. So initial capacity is simply the capacity at the time the hash table is created. By default, the initial capacity is 16 and it can be always represented in the power of 2, like 2, 4, 8, 16, and it will reach maximum till to the power of 30. Load factor is a measure of how full the hash table is allowed to get before its capacity is automatically increased. The default load factor is 0.75. Rehashing can be obtained from the product of initial capacity and load factor. The index of bucket can be calculated using the below formula n-1 ampersand of hash, where n is the capacity and hash is the hash code of key object. The HashMap uses array of buckets or bin to store the elements as key value mapping. Each element can be represented as node and it is implementing entry interface. It has 4 fields as shown below. The hash will decide the bucket location, key and value are the values provided by the user, and next will hold the reference of the next element or it can be null initially. The put method is used to store the key value mapping. The key and value can be the primitive type or it can be the custom key. If we are using the custom key, it should follow some rules to implement equals and hashcode method, as well as the key should be immutable and it should implement the comparable interface. This will help to resolve the hash collision. As we can see, the put value internally calls the put value method. The put value method has two additional parameters, the only if absent. If it is true, it means we cannot change the existing value. So by default, the HashMap uses this value as false. The second one is await. If false, it means it is in the creation mode. So it uses this as a true. Put value also uses the hash method. The hash function can be computed using key.hashcode and it spreads the XOR higher bits of hash to lower. Because table uses power of 2 masking, set of hashes that vary only in the bits above the current mask will always collide. In such scenarios, red-black tree is used to handle large set of collisions. So if key is null, it will be stored always at the location 0 and In another case, it will calculate the key dot hash code and XOR the value 2 to the power 4. And this is how it will calculate the hash index. So this hash method is very important in calculating the index for bucket. Get method is used to retrieve the value for a given key. If key does not exist, it will return null, otherwise it will return the value. I have used Visual Studio Code to explain the concept of HashMap with example. The first use case is HashMap allows only a unique key. It does not allow any duplicate and it allows only one null key. Let's define the instance of HashMap as shown. We are storing the null key with value Bangalore. If we execute this code, we can see the null key with value Bangalore is stored. Next, let's insert another key as null and value as null. If we execute this code, here we can see the old value is lost. So HashMap allow only one key as null, and if multiple null keys are there, it will replace it with the latest value. The second use case is HashMap allow multiple values as null. The map has already one null key entry with null value. Let's insert two more percent object with null values. If we execute this, job map can be seen with three records and all the three different keys holding the value null as seen here. The first value is null null with null key and null value. Second P1 object with age 100 name and the value null, and this one is the third. These values are coming like this because I have given two strings for the percent object. Use case 3. Put method as return type with previous value. I have commented out all the previous code. Now let's insert one null key with Hyderabad value. If we execute this code, we can see the value null is written although the value Hyderabad is there. Why it happens? Because the key null is inserted first time, it does not have any previous value. To explain it in more clear way, let's insert one more record, one null key with value Bangalore. I have commented the previous line so that we can only get once the print statement, and here the value null with Hyderabad key is inserted as a first time, and the second time now we are inserting the value Bangalore for null key. As we know, HashMap does not allow duplicate values, so the null key will replace the value Hyderabad with Bangalore, and if we try to return the value, we will get the value as Hyderabad. The put method will always give us the previous. Use case 4. Get is used to get the value for a given key, otherwise it will get the value null. Let's execute this code. We have one key as null with value Bangalore, and if we want to get the value for null key, we will get the value as Bangalore. Let's execute this code. As we see, we got the value Bangalore. Now let's insert one more record with percent P1 and value as null. And if we want to get the key for P1, the value is null. So we will get the null value. Let's try to get the value of key which is not existing in the map. P2 object we have created and we are trying to get the key for P2. As it does not exist, we will get the value null. In some cases, we are not very clear like when the value of key is coming as null or the value itself is coming as null. In such use cases, we should go for contents key method. The contents key method will return true if the key exists or return false if the key does not exist. So with this statement, if we execute the code, we can get the value false because this P2 is not exist. I hope this will help in getting the clear understanding on the different use cases for HashMap. Let's discuss for hash collision in HashMap. Before this, we will try to understand some concepts. We know HashMap allows unique key, which means no duplicate of keys are there. But what happens once the user try to insert the same key? In such scenarios, the same key will replace the old value with the latest value. Now discuss about the bucket index location. We know key of hash code is used to calculate the index of bucket. There are three possible scenarios for the keys. Once the keys are stored in map, it can be poorly distributed or it can be well distributed and it can be randomly distributed. We know HashMap allows unique key. It means there are no duplicate keys. So what happens when the user is trying to insert the same key again? In such cases, the HashMap replaces the old value with the latest value. We also learned how the bucket index can be calculated. It can be calculated using the key of hash code. If the key uses primitive data types such as a string, the Java will take care of proper distribution of hash code among the as the string class is immutable. In case of custom keys, the key may be poorly distributed, it can be randomly distributed, or it can be well distributed. Now let's say we want to store the custom keys in the map and we have defined the rules for the custom keys as discussed previously. But due to some reasons, the logic of equal and hash code might not be efficient, or the key might not be immutable, or it might not have used a comparable implementation. In any of such cases, let's say the keys are not well distributed and different keys are trying to get the same hash values. In such scenarios, the hash collision will happen. Let's see this with an example. An instance of job map with default initial capacity is created to store person as a key and city as a value of a string. So HashMap will create 16 bucket location. Let's create 5 objects for person key. Let's insert now the first element in the hash map. The bucket index location can be calculated with the below formula. Index is equal to n minus n ampersand of hash. Let's say the key of hash code is 7676767 and 16 is the size for initial capacity. So the bucket index location can be calculated as 15 and it can be stored at location 15. The second element, the bucket location similarly can be calculated as 6, so it can be stored at location 6. The third element, it can be stored at location 14. Now for the fourth element, we can see again the key is although different, but we got the same hash value. So here the collision will happen at location 15. In such cases, so the HashMap will store this element as a linked list with the first node holding the reference of next element. Similarly, for the next fifth object, again it's a different key but we found the same hash value, so the collision happened. It is kept in a linked list by again keeping the position of p5 in the second element. I hope this will make you understand how the hash collision is happening. If there are more elements which are getting collision, the HashMap will use tree to resolve this. We can discuss in the next slides about the trees. HashMap uses red-black tree in case of hash collision or if there are large number of elements in the HashMap. Red-black tree is a special BST where the elements in the left nodes are smaller than the root node and elements in the right sides are greater than the root node. Red-black tree has one additional attribute which holds the color for The tree, it is red color or black color, and it follows some rule for inserting the elements based on these colors. Compared to BST, it allows maximum 2 rotation at a given point of time. So it is comparatively faster than BST, and the tree node can be represented as shown here. It uses parent, left, right and previous node along with the flag red. This flag will help to maintain the red-black tree with red and black color. The bin count threshold for using a tree instead of linked list for a bin. Bins are converted into trees when adding an element to bin with at least 8 nodes. The value must be greater than 2 and it should be at least 8. This is very important in doing the calculation for converting a bin from linked list to tree. And tree-fi threshold is quite similar to tree-fi threshold. In this case, a bin can be converted from tree back to the linked list. The bin count threshold for untreefying bin during resize operation, it should be less than 8 and maximum 6 in case of removal or something. So let's say if the shrinkage has happened and it is keep on reducing. So it needs to check if the count is at most 6, it can convert to the linked list. Minimum tree-fi capacity is the smallest table capacity for which the bin may be tree-fied, and it is default capacity is 64. Mod count, the number of times the hash maps has been structurally modified. Mod, Mod count is used to find how many times the hash map has been modified. It can be due to the rehashing or it can be due to some removal of operation, etc. This field is also used to make iteration on collection view of HashMap fail fast, which we can see for concurrent modification exception. As we have understood what is hash collision and we have seen this, let's consider the case that minimum tree capacity equal to 64 has been reached and there are 8 elements in bucket location 15. So tree-fi threshold condition is met and linked list in the 15th bucket location needs to be converted to tree. Let's see below 8 values we need to store in the tree. Red black tree works on below rule. Rule 1. If tree is empty, create new node as root node with black color. Rule 2. If tree not empty, create new node as leaf node with red color. Rule 3. If parent of new node, black, exit. Rule 4. If parent of new node is red, checks parent sibling of new node. And here we have two options. 4A. If black color, perform rotation and recolor. 4B. If red color, perform only recoloring. Check whether parent's parent node is root. If not root node, recolor and recheck the node. Let's see this with the given example. Let's discuss this with an example. First element is 20. As 20 is the first element and tree is empty, it follows the rule 1. Create new node as root node with black color. Step 2. The next element is 15. 15 is smaller than 20, so it will become the left child for node 20 and it satisfies the rule 2. If tree not empty, create new node as leaf node with red color. The next element is 30. As 30 is greater than 20, it will become the right child for root 20 and it also satisfies the rule 2. If tree not empty, create a new node as leaf node with red color. Step 4. The next element is 25. 25 is smaller than 30, so it will become the left child for node 30. As we can see, it violates the parent-child relation with red color, so we need to follow some rule. If we see the parent of new node is red color and parent sibling is also red color, So we follow the rule 4b. Only recoloring is required. So we have recolor both the parent node and the parent sibling nodes, that is 13 and 15. Step 5. The next element is 28. It should come as right leaf for 25. As the tree is not empty, it satisfies the rule 2. It should be created as leaf node with red color. As we can see, it violates the property of parent-child relationship as it has red parent-child. So we have to apply some rule to make it red black tree. Since the new parents node has no siblings, rule 4a will be applied. It says we need to do rotation and recoloring. Since node 28 is right node of 25 and parent of node 25 is 30, here we have RL relationship. So we need two rotation. First we will perform the right rotation and then the left rotation. The right operation performed on node 28 and 25. 28 moves upward and node 25 moves downward. Above tree still has red conflict. Now we can do the LL rotation. We need to perform this operation. 28 is median and 28 will become the root node and 25 and 30 will become the left and right child. After rotation, node 25 and 28 needs to be recolored. Now the tree looks fine and we are fine with this step. Step 6. The next node is 45. It should come as right child of node 30. It also follow the rule to mark this color as red with the leaf node. Again it violates the red relationship for parent and child. So we need to follow some rule. As for 45, the parent node is 30 and it has a sibling 25. So it goes with the rule 4b. We need to recolor the node 25 and node 30 as black. Now the tree looks fine, so we will go with the next step. The next step is 10. It is the left child for node 15. It again follow the rule to create new node as leaf node with red color. As the parent of 10 is 15, it is already in black color. It is fine. So we will go with the next element. The next element is 16. 16 will be the right child for node 15 and it also follow the rule 2. Create new node as leaf node with red color. Again, the parent for 16 is node 15 which is already in black color, so we are fine. And so on. So this is how we should insert the element in red black tree. So as we have seen, in worst case, if we need to do the rotation, it will take only two rotation, either RR rotation, RL rotation, etc. When bins get too large, they are converted into bins of tree node. Bins of tree node support faster lookup when overpopulated. Tree bins are ordered primarily by hash code, but in case of ties, if two elements are of same class C which is implementing the comparable interface, then compare to method is used from ordering. HashMap checks generic type via reflection to do validation. The worst case complexity of tree binary is log n when keys are distinct. hashes are orderable. Because tree nodes are about twice the size of regular nodes, we use them only when bins contain enough node to warrant, like it has obtained the tree-fi threshold, and when they became too small due to resizing or removal, they are converted back to plain bins. One more important thing needs to be noted: the hash code will not be calculated every time for the same key. HashMap will use the same hash code for retrieval, for deletion, for search operation once it has calculated using the put method. As we have seen, when number of entries in hash table exceeds the product of load factor and current capacity, the hash table is rehashed. Internal data structures are rebuilt so that hash table has approximate twice the number of buckets. For example, for default initial capacity, when number of nodes in HashMap is more than number of its total capacity, resizing happens. As HashMap uses power of two expansions, the element from each bucket start at the same index, or it can move with the power of two offset in new. Let's consider this with an example. So the threshold is calculated as 16 into 0.75 is equal to 12. So when the 13th element is inserted in the hash map, the automatic resizing will happen and it will create a new array with double of its capacity, that is 16 into 2 is equal to 32. And again, if we calculate the product of these two, the threshold value is 24. So when 25th element is again inserted into the hash map, automatic resizing is required and again the hash map grows double of its capacity with 64 and so on. In such cases, after certain period of time, if the values are keep on coming, the hash map has two choices. First, as it can go with the same way by going with the automatic resizing. Next, it can try to see what is the tree fi capacity and the threshold. If both of these conditions are satisfied then it will convert the linked list into the tree node. For calculating performance, there are three main things which we need to consider: the load factor, initial capacity, and the key. So we have two options here. Option first, initial capacity can be chosen as maximum to avoid rehash operation. If the initial capacity is greater than maximum number of entries divided by load factor, no rehash operation will even occur. So let's say for 1 million record, it means there are 10 lakh records. And if we do the calculation, 10 lakh divided by 0.75, it is coming approximately 13 lakh 33,033. In such case, if we will choose initial capacity at least as 13 lakh 33,034, no rehashing will happen. Now option number 2 is HashMap internally rebuilt structure as tree node instead of linked list to get the better performance. If the performance degrades gradually if the hash codes are poorly distributed. In such scenarios, there are more chances of hash collision because many keys are sharing the same hash code. In case of well-distributed user code, trees are rarely used. If the hash codes are randomly distributed, the hash map follows the Poisson distributions in the bins. So it is very important that a custom key should follow some rules, like it should be immutable, it should follow equal and hash code implementation. It is very important to implement comparable interface from Java 8 onwards because HashMap internally uses tree in some scenarios. In such scenarios, compare to method is used for ordering and putting the elements in the tree. So these three are very important from the user key perspective. Okay, so let's revise again. So we have understood hash collision occurs when two different keys have equal hash code, and from Java 8 onwards this can be resolved using tree. When the elements are removed from the hash map, the element size is reduced and this is called as shrinkage. When the conversion happens internally in hash map from linked list to tree or vice versa, a split will happen. We can see now the time complexity for linked list and red black tree. The time complexity for linked list in average and worst case scenarios for insertion and deletion is order of 1, while for search it is order of n. And the space complexity in case of average and worst case scenarios for all insertion, deletion and search is order of n. For red black tree, the time complexity for insertion, deletion, and search in average and worst case scenarios are order of log n, and the space complexity for average and worst case for insertion, deletion, and search is order of n. Thank you for watching. Keep watching, keep learning. We'll meet you soon in the next tutorials. Thank you.